Recorded is rolling. It is Friday, September 23rd. You guys remember yesterday you were doing this Atwood Lab. You guys remember this in both halves? Right. Had a pulley, had some lab masses. In one of the setups, you had a Hot Wheels car. Right. You guys remember that? You were figuring out, well, if it goes so far and so much time starting from rest, you could calculate the acceleration. And you were trying to figure out what's the relationship between each of these input masses and the acceleration of the system. So I'll go over the answers with you guys. That was this page you're working on. Okay. But after I go over the answers, hold on to this page because next week we've got some fun activities coming up, including a friction lab, which is printed on the opposite side of this page. Right. So hang on to this page, and I will eventually pick this up from you guys sometime next week after we do the friction lab. Right. Then we're going to solve one problem, and then we're going to finish the rest of the class with a bunch of demos. Okay. Sound good? All right. Right. So the first setup we did with the Atwood yesterday was the classic double elevator setup. Okay, had a couple of different masses here. Okay, let it go and started accelerating. Because if you had the same mass, and that may have been one of the things you tried, you put like 200 grams, like boom, boom, right? Then it didn't move at all, right? So the acceleration was 0. Okay? And you can pretty well figure out if you put all the weight on one side and had an empty string on the other side, it should accelerate at the full rate of gravity. So what if you had two masses that were slightly different, like hook, hook, and then tag this guy right here. Then it would accelerate maybe kind of slowly. Right? That should accelerate. I wonder what that acceleration was. Well, I will show you guys the answer from a free body diagram point of view. I'm going to derive the answer with free body diagrams. The day before you guys did the lab, I actually set up the free body diagrams with you guys on that PowerPoint. You guys remember that PowerPoint? It's also posted to Google Classroom. Okay. Right now, I'm going to do something that I probably won't do super often with you guys, but maybe time to time, which is solve this in terms of variables. Okay. But then after that, I'll go solve this with some numbers with you guys. Okay. Right. So I'm going to call this some general M2 and this some general M1. Okay. M1 and M2 could be anything. Okay. Maybe 100 grams and 200 grams. Maybe it's 200 and 210. Right. It's two different masses. Okay. And let's look at what the forces would be on these masses. Okay. So this M2 has a weight that's pulling it down, like a gravity force. Okay. I'm going to label that M2G, right? M sub 2G, right? For the weight of that object, right? Mass times gravity field. Right? And I'll do the same thing for M1. Now, because M1 is smaller, or I've drawn it that way, I will label a smaller weight. Call this M sub 1 times G. Okay. So I got a couple of force vectors. Okay. Now, actually, I can solve for the acceleration of the system, like the downward acceleration of this and simultaneously upward acceleration of this with just that. I don't have to label anything else. Okay. But you guys know that there are other forces going on. Like if you hone in on either mass, there is a tension force that's pulling up. Okay. And we walked through this thought process yesterday. Well, this tension force must be the same for both of them. I'll call it F sub T, force due to tension force. Okay. And see how it's like the Goldilocks force? Okay, so first of all, it's the same on both. But see how it's larger than the weight of M1? Right, so that's going to drive M1 to go up. Right, but it's also smaller than the weight of M2. Look at that. Right, so that M2 has a net force downward. And so this whole thing's going to accelerate clockwise. Is that right? Now, tension force is just internal to the system. So there are different ways of going about solving this. I'm going to show you guys the way that I like to do it myself, which is look at this from a macro point of view and just say that the two weights are the external forces that drive the system. Let's kick over to Newton's second law of motion, which you guys will remember is printed on the back of this packet. Okay. By the way, next week we'll do some Kahoots that involve these other questions that we haven't hit yet. But on the back, Newton's second law of motion. You guys remember F equals ma? A lot of times it's said that way. I'm going to use the fraction form of it. Why does anything accelerate? Well, because there's a net force acting on a mass, right? So just this rearrange. All right. So I've got the acceleration is equal to net force on some total mass. Right? And if these guys are playing tug of war, right? M1 says, let's go counterclockwise. And M2 says, no, let's go clockwise. Right? You could put it in a straight line like a rope, but just wound it around this frictionless pulley. then I'm thinking that the net force is going to be the difference between those two, isn't it? Okay. Whatever this number is minus whatever that number is. Okay. And again, I'll do this in terms of variables. I think you guys will be able to digest this. And so whatever weight this is minus whatever weight this is. You guys know that m times g represents a gravity force, right? Okay, so that gravity force minus that gravity force, the difference is the net force. Okay? Okay, guys follow that? Okay. And how much total inertia is being moved around by that net force? Well, isn't it just both of the masses? Okay. And mass is a scalar value, which means I just have to add everything up. Right? See, force is a vector, so it can add or subtract. In this case, it's subtracting because they're disagreeing about which way to go, right? Clockwise or counterclockwise. But the masses, well, that's just some total inertia that's being moved. So isn't that like the sum of the masses? Like that? Right? In fact, that right there is the answer. The difference is some number of newtons, some two different weights. Weight 2 minus weight 1 is the net force. And then the sum of masses is just you add the masses together, m2 plus m1. Okay. I could throw another step in here, which just make it look more like your lab. Could I factor out the Earth gravity and do difference of masses over the sum of masses times gravity? To do that. Okay. Now, I guess it's not super necessary. These two steps are the same thing. Okay. But the reason I'll do that is because you may have gotten that as your answer. In fact, if you did, you got it exactly right. Remember the box numbers, this find a relationship among A, the actual acceleration you found empirically through kinematic motion, G, the free fall gravity, 980 centimeters per second squared, and M1 and M2, the input masses. Okay. And I said using the starred columns, and I was giving you guys a huge hint. I was saying if you multiply or divide these first three columns, there's some way it should land you pretty close to the actual acceleration that you found empirically. Okay. And this is it. Look, it's the difference over the sum of masses all times Earth gravity. Right? Okay. Let me see. Show of hands. How many guys got that? How many guys got that? Ooh, oh, all right. So some of you guys did. Awesome, awesome. Right. So that's the general answer to that one. Okay. While we've got the double elevator Atwood out, I want to do something special with you guys. I'm going to pull a problem from my honors classes with you guys. And we're going to do this. Okay. Hey, look at that. It's a double elevator Atwood. Okay, kind of a weird like 3D perspective on it. Okay. Got a pulley, a couple masses. We've got 5 kilograms and 3 kilograms. And they're asking two things. What's the tension in the rope and what's the acceleration of the blocks? Downward acceleration of the big one, upward acceleration of the small one. Okay. Now, notice my setup really only answers one of those. It answers the acceleration question. So I'm going to do that first. I'm going to answer these questions in reverse order. There's a different way to approach this where you solve with the tension first, but I'm not going to worry about that. So what if this was like 5 kilograms and 3 kilograms? Let me pop in the numbers. Let's call this 5 kg and 3 kg. Right? So you guys see those masses are 5 and 3 kilograms. Is that okay? Right. So if I kick over here, I'm actually going to go back a step to this step and do it this way. Okay. Guys, 5 kilograms. How much weight is that? What's 5 times 10? 50 newtons. Isn't that 50 newtons of weight? Say, let's go clockwise, 50 newtons, right? Okay. So the acceleration is, I got 50 newtons minus, okay, if this guy's 3 kilograms, what's his weight? 30 newtons. Ah, you guys see a 20 Newton net force, right? 50 minus 30, right? Okay. Hey, acting on how much mass?
5.
5 plus 3. Ah, you guys see 5 plus 3, right? 5 plus 3. Okay.
8. 20 divided by 8.
Exactly. Yeah. Okay. So you're right. We got a 20 Newton net force. Okay, these guys are fighting each other, acting on 8 total kilograms. Right?
55.
Yeah. There we go. You guys beat me to it. 2.5 Newton per kilogram is the same thing as meters per second squared, which all describes an acceleration.
So that's the only formula we have to use?
Yeah, just F equals ma,
Oh,
right? There you go. Yeah, so that's where it started, right? It started with Newton's second law of motion, and then,
It's like the rise over run thing, huh?
yeah, I guess it, this kind of is, right? Like, it looks like, yeah. Okay. All right. Now there was a follow-up question. Again, this comes out of the honors text, but I want to do this with you guys, right? Actually, it was the first question they asked. What's the tension in the rope, right? Which I have not addressed yet. Okay, you guys see this tension force? Okay. Well, I haven't shown you guys exactly how to get it, but we have sort of framed it. You guys remember it's like the Goldilocks force, right? It must be larger than the small weight, but smaller than the large weight. Oh yeah. Yeah, okay. And we know what those two weights are. They're 50 newtons and 30 newtons. How many guys think that the tension must be somewhere between 30 and 50 newtons? It's got to be somewhere in there, right? I think it's probably pretty close to 40 newtons. Maybe not exactly 40, but probably pretty close to 40. You guys think? Because that's the only thing that would make sense. So there would be a net downward force on M2, but a net upward force on M1. Probably pretty close to 40. Okay. So how are we going to figure that out? Well, we're still going to use Newton's second law of motion, but instead of looking at the whole system from a macro point of view, we're just going to hone in on one of those masses, one of those, right? Okay. We can pick either one. We're going to get the same answer because same tension. But any, meeny, miny, mo, let's say I pick the M2. Okay, so I'm going to pick the M2 to solve it from that point of view. So I'll do net force is equal to mass times acceleration. Okay, but I'm just going to focus on that M2. Okay, so I'll subscript M2. Okay, now what is the net force? Well, let's say I call it down positive so that I'll have all positive numbers because it's definitely moving in the positive direction, right? That downward direction. Okay, so wouldn't that be its weight minus the tension force? Okay, so I've got, and what was its weight down equal to? How many newtons?
5.
5 times 10 is
50.
50. Isn't that 50 newtons downward force? Right. You guys remember before, right? 50 newtons weight. Okay. So I've got 50 newtons of weight minus the tension force acting upward. We call it up negative. That's why I'm subtracting, right? Because they're fighting each other. Okay. E is equal to, again, I'm just focused on a single block. And that block is 5 kilograms. That's why I'm plugging in 5 kilograms. Okay. So this is not macro point of view. This is like a micro point of view. I'm just focused on a single block, right? 5 kilograms. Okay. And I know how much it's accelerating because I already figured that out. I figured it out from the macro point of view. Remember, it had to be 2.5 meters per second squared. Okay. I really should put a direction on this, but the directions are opposite for the blocks. For the large block, it's downward. For the small block, it's upward. And from the system point of view, I might call it clockwise, right? So this is 2.5 meters per second squared. And since I'm calling down positive, the positive direction, it's positive. That's positive. And then downward force minus upward force. Right. Okay. You guys get that?
Mm-hmm.
All right. So that's the entire setup. And now to finish this off, it's just few algebra steps. So let's see what's 5 times 2.5. Here, got 50 newtons minus the tension force is equal to 12.5 newtons. Right? Oh, I'm gonna how about add the tension over and subtract the 12.5 over? Okay. So that's gonna give me tension force is equal to 50 newtons minus 12.5 newtons, right? Little algebra swap. Swap stuff around. Then what's 50 minus 12.5? I'm getting the tension force is 37.5 newtons. There you go. Okay. That's the tension in the string. Hey, remember even before we started plugging and chugging or setting anything up, we said, well, it has to be between 30 and 50. Right? It has to be between these two. That's the only thing that makes sense. That's the only thing that's going to drive the small one up and the large one down, is it has to be between those two weights. I said, it's probably pretty close to 40, maybe not exactly 40 newtons, but probably pretty close. And in fact, it is. Okay, that's pretty close to 40 newtons. Like I said, all good. All right. There was a second half of your lab, which was this modified Atwood. Remember, you slip a hot wheels car in here to get rid of the friction and then just let this weight, M1, the weight of M1 pull down. Okay. All right, so let's do that one. Okay, no, I'm going to take you guys through the same thought process, except the setup's a little different, so the outcome's going to be a little bit different. Okay, let's that picture going again. Big ol' M2, which includes the Hot Wheels car. Right? If you remember to add 30 something grams for the Hot Wheels car. Okay, you got a little tiny M1 down here. Okay. In fact, if you did that, if you had a big ol' M2 and a little tiny M1, that would have caused it to accelerate pretty slowly, which would make it easier to time. Guess what? Okay, so let's see. I know that this M1 has some weight. I'll call it M1G. Okay. Same thing. I'll solve it in terms of variables because it's just a couple of steps. Okay. Now, really, that's the only force that matters. Like, there are other forces. I'll go ahead and draw them in here, but M2 has a big old weight, M2G, but also a normal force that's exactly balancing that out. Oh, it's going off my page there. Oops. Okay. Force normal. You guys see that now they're going to cancel out, right? Okay. There's also a tension force, F sub T. F sub T. Okay, but that's just internal to the system. All it's doing is just holding the system together. Okay. The only force that's acting as an external force that is going to drive the system to move is the weight of M1. Okay. Okay. So let's kick over and set up Newton's second law of motion. The acceleration of the system is a net force acting on a total mass. That's Newton's second law of motion. Forces on masses cause accelerations. Okay. And since the question was, what is acceleration? Right? Well, the net force is the weight of M1. That's the only one that's driving the system to move. Right? So I'll call it M1G. And how much total inertia is being driven? How about the sum of these two masses? Right? They're both tied together on the same string, so they're both moving together. They have the same acceleration magnitude, just a little bit different directions, but yeah. In fact, that right there is the answer. Okay, that's it. You know, just a couple steps right there. Boom, boom, done. Right? It's the weight of the hanging one divided by the total mass. That is the acceleration of the system. Okay? You guys can check your numbers too, because you guys have empirical data in front of you. Okay? So, in fact, if you do that, and I was giving you guys a hint again with the starred columns. Okay? So if you take the mass of the one hanging, divide by the combined mass, and then multiply that all by Earth gravity, I bet you'll get a number that's kind of in the ballpark of what you got for the acceleration. Okay, you guys okay? Okay. Any questions so far? Questions? All right. So here's what we do. I'm going to kick over to Paul Hewitt, and we're just going to do demos for the rest of class.